Pamela Martin is an assistant professor in geophysical sciences at the University of Chicago. Her research focuses broadly on reconstructing changes in deep ocean temperature, chemistry, and circulation to understand oceanic controls on climate change. She is interested in the links between ocean cycles, atmospheric carbon dioxide, and climate change on timescales ranging from that of a human lifetime to hundreds of thousands of years. Her research techniques include measuring the chemical composition of fossils and formulating computer simulations. In 2006, Dr. Martin co-authored a study showing how the food that people eat is just as important as what kind of cars they drive when it comes to creating the greenhouse gas emissions that many scientists have linked to global warming. This study has led Dr. Martin to additional work on food production and the environment, including a field study begun in 2009 to assess the energy efficiency and greenhouse gases associated with food from small-scale diversified farms. Please join me in welcoming Dr. Pamela Martin.
Hi, well, thank you. It's a bit intimidating to talk to a room full of teachers, educators who are much better trained in this than I am. I came more from a research background, and I'm really excited to be talking to you today. It reminded me, the introduction just reminded me, and putting this talk together, of kind of how all my diverse research is related. As Jamie just said, I actually started out looking at past climate change. I'm interested in the global carbon cycle and how that affects temperatures, and particularly what role the ocean has in regulating climate and water, as we're talking about today. And I was putting this talk together, I saw how I have feedback here, I'm so sorry. Okay, I'm sorry, I'm so not used to talking with a microphone. Even in a big classroom, we just end up shouting. So what was amazing is that I get to talk about the cycles, the natural cycles, which is what really got me interested in sciences in the first place, although I was always interested in the environment. And so as I went through this, I realized I end up where I am today with my research, and that is looking at the environmental impacts that we have on the natural cycles. Now, I started out here with my title is From Clouds to Sea, and that's really a mid-continent perspective of the water cycle, because as we've been having all of these storms these last few weeks, it's been clear what the role of the clouds has been in our hydrologic or our water cycle. But I actually wanted to start out thinking about it from a different perspective. Because it's a cycle, we can start at any one point. And rather than thinking about from clouds to the sea, I actually want to start you out for a second on seas to the clouds. And this is about one of my favorite water cycle portions that I really enjoy. What you're looking at here is a picture of the coastal redwoods in California. And you can see the fog in the redwoods there. And actually, this fog is the source of water vapor. So while we've been having all these storms and thinking about the precipitation, actually what keeps the redwood forest going are the fog. And it's a really neat little part of the water cycle. And if we look here at this very first slide, what we see is the summer mean fog frequency here on the left. You can see in the middle slide, those little dots represent all the places where the redwood forests are. And at the end there is a picture of the coastal California inundated with fog. And this is a very classic water cycle story. So here we're along the coast, so we have to move ourselves to coastal California. And what we see is the waters along the coast there, with winds blowing downshore, cause upwelling of cold waters. Now, we're in California, and we all think of California as warm, and so we can think that the land is heating up warm here, and the sea is heating up warm here, except for where these cold waters from below are coming up. These cold waters create a cold surface layer. You have water vapor, and that water vapor moves inland. And it's this water vapor and those fog, the clouds, the surface layer clouds, that are actually maintaining the redwood forests of California. So this is an example of from sea to clouds. So it goes from the sea up to the clouds and inland. And these clouds make their way all the way through to the mid-continent, to where we are, to get us into the more typical part of the water cycle system that we think about, and that's the rains, and the precipitation, the evaporation. It's been quite humid lately, so we haven't had much of that evaporation. But so this gives us a more global perspective. Now we've moved away from the coast, and you can see all the different hydrologic cycle or water cycle components. Now, I know we've all had this years. We first see it now, I think, in the lower grades. In second and third grade, we start talking about the water cycle. And all the way up, we revisit it. And we continue to revisit it in college and in graduate school even. So what I want to talk to you today about are just a reminder of what the different components are in the water cycle, the reservoirs, movement among these reservoirs, the storage, and I think for a matter of time, I realized I had a little less time, we might skip the idea of residence time. And then I've switched this around a little bit. We're going to talk about water and climate, because that really demonstrates how water is a limited resource. And then finally, think briefly about an environmental framework for thinking about water, as that can help to put into perspective what we're going to hear over the next couple days. So I want to start out here with the reservoirs. So there's a lot of sexy diagrams out there of the hydrologic cycle, but I always find that it's much better with this, to think about it in something that we can all draw, that we don't need to be an artist to draw. And so here's a very simple depiction of the hydrologic cycle. And what's represented in here are reservoirs, places where the water is stored, and then processes that move the water among the reservoirs. So let's first just think about those major reservoirs. The first is ocean storage. And here's just a question: what percent of the Earth's water is stored in the oceans? And actually, most of the Earth's water is in the oceans, most of it that we can have any sort of thinking about for our global cycle. And nearly 97% of it is in the oceans, and that only leaves a little bit of water. That's the freshwater part. Here we have about 3.5% of the Earth's water is actually fresh water, and the rest of that is the ocean water. Now, we know the ocean water is saline water, so it's not a direct reservoir that we can tap into for many processes, but we still want to think about that as being the reservoir, because ultimately when we're thinking about from clouds to sea and back again, what we have is this big ocean of water where we can evaporate that water from to drive some of the cycles on the continents. Now, I want to think about for a second the limitations of the ocean as a reservoir. And the first thing to think about is is the volume of the world's oceans constant? Does it ever change? And on the time scales that we're experiencing, there's actually a small change in the volume. But that change in the volume is because we're heating up the oceans. The oceans heat up a little bit, warm waters expand, and so we actually get a little bit more water. Now, not in mass, but just in volume. But if we go back through time, we can see that there have been some changes in the world's ocean. So 20,000 years ago, the oceans were lower. They were about 400 feet lower. And that gets us into another one of the reservoirs for water storage, and that's the ice and the snow. So 20,000 years ago, instead of 400 feet worth of water being in the oceans, it was actually stored on the continents in terms of the ice and snowpack, primarily in these large ice sheets that covered where we are today. If we go back further to a time that was slightly warmer than, at least warmer than it was before we've started our path towards global climate change, sea level was actually slightly higher than it was now. So we think we had about 20 extra feet of sea level if we go way back about 120,000 years. But we still had ice then, so we call it a glacial interglacial cycle. 20,000 years ago, this big ice sheet was the maximum, where we had maximum storage of fresh water in ice sheets. But we can go back 120,000 years ago. We still had some ice like we do today in Antarctica and some in the North Atlantic. The Arctic sea ice was still there. But if we go back 3 million years ago, we didn't have a big storage of ice on Antarctica. And so the sea level, we even had nearly 200 extra feet or 150 extra feet on top of that 400. So what that's telling us about, actually, is the storage of water as ice and snow. So we have glaciers, ice fields, and snow fields are all storing a big part of the fresh water. So we said we have a little more than 3% of the ocean's of the Earth's water as fresh water, and of that fresh water, nearly 69% are glaciers and ice caps. Just under 2% of the Earth's water are actually locked up in ice and snow. Now, some of that is slowly melting from natural climate change, and it fills the streams in the surface water, and it actually has been melting for a long time and filling groundwater reservoirs. So the groundwater reservoir is the next reservoir we need to think about. And for the groundwater, here we have, it's about 1.5 of the total water supply. It's about 30% of all of our fresh water is in groundwater. Now that groundwater, if we think about it just for a second, where it came from. And I just said a minute ago that 20,000 years ago we had these large ice sheets and that they melted away towards today, to this interglacial that we're in. And part of that melting went out through surface waters to the sea, and part of it actually filled our aquifers. So we have aquifers of fresh water that were deposited a very long time ago. Essentially, this is fossil water. And this starts to set us up for putting water issues into a framework, which we'll talk about at the end of the talk. So we have groundwater aquifers that actually were recharged by these melting glaciers. We have these fossil aquifers. And then on top of that, we actually have surface waters. And those surface waters also help to recharge the aquifers. So we can think about that groundwater supply in two different ways, as that fossil supply and as that more renewable supply. So that's water as a resource. If we look at surface waters, fresh water, as we have been saying, is about 3% of all the water. And surface waters that we see in the lakes and in the streams are less than 1% of all of the fresh waters. In fact, they're less than 0.5% of the fresh waters. They are a very small part of it. And it's the part of it, this small part of it, that we often think about the most when we're thinking about the water cycle. We think about the lakes right here, Lake Michigan. We think about the streams that flow, like the Mississippi. This is a very small part of it, and it's actually a part of it where we've really had a huge impact. And when you have a small part of it, it would only take a small impact to actually change that. But here, it's one of the most impacted of our resources. So if we think about how we've impacted our resources, we have the surface waters, and we can kind of go in reverse order now. So we've really impacted these surface waters. They're exposed to all of our activity. We have groundwaters where we have the two different types. We have this fossil aquifers that we can think about part of that water being recharged a long time ago, and part of it that is part of our modern cycle that we'll continue to get into in a moment. But we have that part of it, and we've impacted that as well. Now, it has a little bit of protection from us because it's groundwater, yet it's still heavily impacted because we draw from it, and we have infiltration through there. And then we're also impacting the ice and the snow. And the ice and the snow get impacted through global climate change. Right now, there's substantial evidence that the planet is heating up. And with this heating up, we're speeding up this natural cycle, and we're actually getting rid of some of the ice and snow that may exist in this equilibrium state. And so we're actually depleting that resource. We're also impacting that resource through pollution, so through burning of fossil fuels with black carbon and with various chemicals in the atmosphere. So those are two different impacts of it. And finally, we have the world's ocean. And given that it only changes by so much for these long time scales, it's really doubtful that our impacts are very large in terms of volume on the ocean right now. However, there are parts of the ocean that can be very sensitive to human impact, those closest to all the activity. And so again, we can influence both quantity, as I said, through this global warming, and that's very small, and quality through the type of the coastal processes. So if we go to our last reservoir now, is one that sometimes we don't think about very much as a reservoir, and that's the Earth's atmosphere. We think about the atmosphere as the air we breathe, but actually it is key in this water cycle for the processes we're going to look at. So it's a very small part of it. You can see less than 0.001% of the water is stored there, but it's an important part of it. So here's just a summary slide of the distribution of the Earth's water. So we have the oceans with this fresh water on top of that, and then we take that fresh water and we can divide it into the fresh water that is kind of somewhat locked away from us, and that's in the terms of ice caps and glaciers and groundwater, but that groundwater we tap into. And then we have the fresh waters, the lakes, swamps, the rivers. And we have these storage reservoirs, and all of them have water stored in them for different lengths of time. And in order to understand that, we need to review, again, just the movement among all the reservoirs. And here is an interesting kind of, just a very simple view. And actually, I didn't realize I had the animation in there, but the point of it is just that it's another one of those simple drawings that we can make. And it takes us from thinking about the hydrologic or the water cycle from being this static storage or reservoirs into a more active model, thinking about the processes that move water about. So we have precipitation, we have the water that's infiltrating, and then we have into the groundwater, and we have groundwater flow, and then we have discharge onto the surface. So we have all these active processes. So we often paint the water cycle as all the reservoirs and what we're doing to those reservoirs, but it's also important to think about it in terms of the active processes. So the key processes that are moving water through the atmosphere are evaporation and transpiration. Now, I'm not sure that we're going to hear a lot about this over the next couple days, and that's why I wanted to just point it out right now, because this is the movement of the water from the sea to the land, and then from the land back to the sea again, that the evaporation accounts for about 90% of that water that's in the atmosphere, that's moving the water from the oceans onto the continents. And then we have transpiration, and that's the plant's role in this. That's like the redwoods in the coastal forest is the transpiration. That's a smaller part overall in the global cycle, but can be a huge part of it for any given ecosystem. So if we go back, and I had another animation that I thought was lost, but this active model of the water cycle, this is kind of showing the events in a setting like the coastal setting, those coastal redwoods, but really is just a smaller it's a microcosm of the larger water cycle. And so we have precipitation events. We can have rain, which we think of a lot because we've had a lot of it here. In the winter, we have the snow here, and the fog and the mist is a key part of it. So that the fog is a part of it that we don't often think about, but when we're thinking globally, this is a very important part of the water cycle. And here you can see the transpiration highlighted by water absorbed by roots. And you can see it going up the tree here. Now, an interesting thing about the coastal redwoods, going back to that very first thing we talked about, is that they actually end up many times taking up the fog through their plant system, and instead of pumping water, and as you see here, they're actually pumping water through the plants into the ground. It can be so overwhelming that their cycle actually works in reverse. And a plant's water cycle is just similar to the Earth's water cycle in that it needs to bring water through the whole plant. So if we look back to the components now, those key components that I highlighted were the evaporation and the precipitation. And there's a couple other processes that we need to think about. And one of them that actually you don't see on here and is often left off of these charts is sublimation. And that's the change of ice directly into vapor. And why this is important is because it's a big part of the globe when we think about going to Antarctica, which we forget about a lot of times. It's on the South Pole, but it's an important storage reservoir of water, and it's a way to get water into the atmosphere in really dry environments. And it's actually an important part of the energy cycle as well as the water cycle. So that's another key thing to think in it. It's not something that we encounter a lot, but it's something that we need to remember. And then we have the groundwater discharge. And the stream flow. The stream flow is pretty obvious, something like the Mississippi. The groundwater discharge might be something that we don't necessarily think very much about, particularly here in the Midwest. A lot of our removal of that fossil water and the recharged water into the aquifers in the Midwest is through pumping, an unnatural part of the water cycle, really. But there's a natural removal of groundwaters from these aquifers, and that's through groundwater discharge, where you can have the topography interact with where the groundwater is going to come out, and then you end up having a spring there. So you have natural discharge from them. And you can have this on land as well as along the continents right into the ocean. So the important parts of the cycle that I want to continue to highlight, though, are going to be the evaporation and the precipitation. But we want to think about storage in the reservoir now that we've talked about movements among them. So we have the movement of evaporation and precipitation, and we have the movement of groundwater pumping, and we have the movement of stream flow. We can think about these when we think about a reservoir as simple accounting. It's a mass balance. And the storage in a reservoir, how much water is there, and the residence time, how long it's going to be there for, is a consequence of those movements, those fluxes between the different reservoirs. And it's very simple accounting. It's the inflow minus the outflow is the net balance. Now, globally, the inflow is evaporation, and the outflow from a system is precipitation. And so we have something E minus P, which you hear a lot when you think about the global water cycle, and the difference between that is the net balance. It's going to tell us about whether a place is generally dry or whether it's humid, whether there's a lot of storage of water above ground. Now, this is referred to as the continuity equation or conservation of mass, but really it's simple accounting. And so I want to do two views of this. Let's start out with this global view of inflow minus outflow, or evaporation minus precipitation. So we can think about this from the global view of the global net water balance. So what's up here, we have three different lines, and so you can see that along the bottom is latitude. So the tropics, the humid, moist tropics, are at 0 degrees there. The North Pole is over there at 90 degrees north, and Antarctica with the big ice sheet on it is there at 90 south. We have the precipitation line there in black, and you can see the precipitation in the tropics. And this is tropical rainforests. We think of the tropics as this moist environment. And then you go down to lower precipitation when you get to these mid-latitudes, and you keep going down towards the high latitudes. Now, the precipitation alone is only part of it. That's the input to the system, or the outflow, depending on how you're thinking about it. And the evaporation is the other part of that balance. So we have evaporation in some places actually exceeding the precipitation. So if evaporation minus precipitation if the evaporation is more than the precipitation, we end up having an imbalance there, and we end up actually losing water from that system. And it's a dry system. Whereas if the precipitation is more than the evaporation, then we have it so that we actually have a net amount of water in the system. So you can see the evaporation minus precipitation, and it predicts where we're going to see the Earth's tropical forests, and it is going to predict where we see the Earth's deserts. So this simple balance of evaporation and precipitation actually tell us the very broad distribution of water on the planet. Now, in a very much more practical, everyday sense, we can think about water, the mass balance of water, as storage. And we go back to this idea of inflow minus outflow, and the balance of that being change in storage. Again, this is still that same conservation equation. But in this case, when we think about it more in an everyday sense, this inflow and outflow might be something like a reservoir. And a really nice example of this is Lake Mead. Lake Mead in the West in May 2000, you can see right here, we have the storage term is what we're looking at. That surface water that we're looking at is the input minus the outflow, and that's going to be the storage in Lake Mead. In 2003, the storage decreased between that time. So again, we have 2000, we have larger, and then you can see the contraction of it. This is a case where the outflow exceeded the inflow, and we ended up drawing down the reservoir. It leaves us to the question of why we have this imbalance. And the imbalance can result from natural variations back to the global cycle of evaporation and precipitation, or it can get to the man-made part of that, and that's the withdrawals from it, the water uses of it. And then, again, there's the third part of it, and that's simply the man affecting climate. So it's a combination of the two of those. Now, to put the limitations of the water system and to think about it as why is it a limited resource, I wanted to actually put it into a broad perspective. Again, I think we're going to get a lot of nice case studies over the next few days, but I actually wanted to talk about it as a big system first here. And that's, what are the limitations? And the way to think about this is to think about water in the environment and climate change. So the temperature, the global mean temperature, or the temperature of one little area, has a lot to do with how much water a given parcel holds, how much water is in the atmosphere. So the typical way that we end up saying this is, is that the water can hold, the atmosphere can hold a certain amount of water. And as the temperature goes up, there's a larger amount of water that can be in there before it's completely saturated. Once it's saturated, then we have precipitation. So with global warming, this simple prediction, this idea of temperature going up, suggests that we're going to have more water in the atmosphere. So that's going to necessarily enhance evaporation. So at higher temperatures, we have we're going to have the top plot there. That's evaporation. So we have two different lines plotted on that. There's a dark line of what it is today. So if we take the water system and look at evaporation for today, it looks something like this. This is our model of what it looks like, so there's some variation in it. And the dark line is modeled for today, and the dotted line is modeled under a global warming scenario. So taking that very fundamental relationship between higher temperatures, more water in the atmosphere, the model predicts more evaporation. And what's interesting is that there's generally more evaporation across the entire planet. So this is a plot like we saw before, where we have the equatorial region in the middle and then the poles out on either end, and the dotted line is nearly above it in all places, except you can see there at 90 north. The bottom line is precipitation. So evaporation has increased. We have a water cycle, the cycle of evaporation, transport, precipitation. So we naturally think that we're actually going to enhance precipitation too. Now, the atmosphere can hold more water, so overall we're going to expect more water in there, but we're also going to have more places where the water comes down. And so the interesting thing is that although the evaporation was nearly always higher, the precipitation is very location specific. In some places, we have more precipitation under scenarios of global warming, and in others, we have less. So it can be either way. So we have to add one more process in here. So we've talked about the water as a cycle and moving through. What's controlling where it's raining? And we have the temperature distribution on the Earth, and we have the winds. And the winds actually are also a function of the temperature distribution. And the precipitation tends to be controlled by that overall wind circulation. So if we want to predict where the evaporation and precipitation balance is going to change, we have to look towards the natural cycle. And what the models show and what makes sense in terms of just speeding up the cycle is that you tend to intensify everything so that the dry areas are going to become drier and the wet areas become wetter. It demonstrates, though, the fact that the water is limited, that we start out with most of the water in the ocean, and we can evaporate some of that to get fresh water, and we can bring that onto the continent, and then it's going to go back out again. We can change the state of the planet a little bit. We can make it warmer. We can change the distribution of the water, but it's not going to change the overall quantity of the water. Now, where is this water going? Well, part of the water is actually in the atmosphere. The atmosphere is going to hold more water vapor, and actually what this is going to end up doing is going to end up producing more warming. And so you get into this feedback of where it's warmer, so you have more water in the atmosphere, and then it's going to get warmer again. And so the system could, it sounds like it could run away. We have some controls on that, such as evaporation and transpiration, but the point is that it is a feedback system. And if we look at where those models are telling us about this enhanced runoff and the change in the balance of evaporation and precipitation, here you can see a world map where the hot colors, the red and the oranges, are where it's going to become drier. And this is an illustration of the idea that the dry areas become drier. So the West in California, where our food shed is right now, is going to continue to dry, like the drought we see today. And Nevada, which is already dry, is going to get drier as well. As we move through the U.S., you can see that in terms of water, the Illinois or the Midwest might actually be a winner in getting a little more water out of the situation. But the problem with this is that it's intensifying the global water cycle. So that would suggest that when we're getting more of this water, we're getting it in these large events. And so a lot of the modeling is showing that it's not just scattered about over the whole year, but actually we get more events like the ones we've been seeing recently, but there's no way to say that those events have anything to do. I think these are just, the summer storms. But it's a good time to be talking about these summer storms because that's what we would expect, enhanced storms like that. So we have the global change, the model runoff, and so that's the surface waters. Now, part of that water is actually going to can help to recharge aquifers. And so we're going to get some of that water running off and some of that infiltrating. And so this actually gets into, I'm not sure how I'm doing for time. I'm sorry. Okay, so this gets into the final idea that I want to leave you with, and that's just an environmental framework for thinking about water. And I tried to lay it out a little bit as I went through, and that's that when you think about water, there's quantity issues and there's quality. The quantity, the volume of the water, the quality, how good it is. And then we can think about the impacts. And it is arbitrary, but we can think about a direct human impact as kind of really what we think about, and sometimes as our worst case scenario. It's affecting us directly. And we can think about the environmental impact. And if we think of any beneficial use of water, so a beneficial use of water could be irrigation for agriculture to provide us with the food that we consume. That's a beneficial use. Every beneficial use has the potential to also be an impact to the negative side. So when we use that water, it can affect the quantity if it's a consumptive use. That means, are we using it and is it not returning to the same way to the natural cycle? For example, have we pumped it out of groundwaters, and have we used it for livestock, used some of it in plants, taken it away out of that ecosystem, and then let it run off in surface waters, perhaps in concrete aquifers? That would be a consumptive use of water. We talk about quantity of using it in terms of consumption, but actually, if we think about quality, well, what happens when we use water? Well, if we think about that same example of agriculture, we end up adding pesticides and fertilizers, and we end up degrading the water quality. So that water quality degradation can impact human health, and it can impact the environment, but it can also impact the quantity, because we degrade the water to a certain point, and it's no longer available for consumptive use. So we have this simple framework of quantity and quality problems with water and human impact and environment, but it's not really that simple. One thing can move to another category. And I just put an example of some effects that we might not think about, and one would be sort of a direct effect of animals, and that's grazing. So here we have the animals actually in the stream, and you can see you have runoff, you have pollution of it, and you also have other possible changes to the hydrologic cycles as a part of this. So here we have the degradation of the quality of the water, and actually we're affecting the natural cycle, the quantity of it, by the runoff. You can see here, it's a little bit hard with this slide, but actually on the one side of the bottom picture there, you can see that it looks like it's all one type of plant. It's all that brownish type of plant there. And here on this side, you see a diverse landscape. This side right here was protected from cattle grazing. The one on the other side was affected by cattle grazing. What that's done is it has changed the landscape. So it's changed the plants that are there. The plants are an important part of that transpiration, that 10% of the cycle. And the water, they actually end up storing water in the plants and in the root system. So the water storage in those two halves of the photo are different. So here, this cattle grazing activity has actually not only impacted the quality, but it's impacted the quantity in the sense that it's changed how water is going to run off and be stored in the environment. Now we can briefly, as we just finish up here, look at a breakdown of water use in consumptive and returned water. Now returned water is water that we've used but we've put back in the system, and it hasn't been modified that much, or at least beyond the point of serving some ecosystem benefits. And so you can see the returned water is primarily thermoelectric. So if we use it for cooling plants or if we use it in dams for electricity, we're not actually using that water in a consumptive way. We're sort of borrowing it from the environment. Now, that can have impacts, but it's not the impact that we can still actually take that water and drink it or have it as a benefit for wildlife. The other impacts up there are the consumptive uses. And you can see that mining and industrial are a small part of the consumptive use, but actually the largest part is agriculture. It's the irrigation of crops. It's the crops that we grow for food directly. A lot of it is the crops that we grow for feed and for the cattle themselves to maintain the livestock. And so all that together is the largest consumptive use of agriculture, and that's something we're definitely going to hear more about. And then what's left at the end there is the public supply and the domestic supply. Together, that's the water that we use. I don't have a lot of time, but I wanted to get to just one picture, these last two pictures. The first is freshwater availability. And this is kind of a complicated looking map, but this is one of the largest freshwater aquifers. It's in the Midwest. And you can see the difference in the amount of water, and it's the saturated thickness. And so those hot areas, again, are the decline in the water from 1990. You can see here, actually, from 1980 to 1997, over on the right side there, that the thickness of the water in the aquifer has actually gone down. And so this is an example, a local example, with global implications. That is that input minus output and what's remaining as storage. The fossil water in this is being used consumptively. We're not actually recycling a lot of that. We're not allowing the water to infiltrate and recharge those aquifers, and so we actually have a net depletion of it. And so this is something on a local scale, and I just wanted to end with one final note, and that's a connection between sort of a local regional scale and the global. And that there are teleconnections. There are connections in the hydrologic system that we might not think about directly in terms of the pathway of a cloud coming up over the land and raining down and moving across the continents. And here, again, is just a modeling study compared to now. And the base map that you see here is the land use. And so we have forests in dark green, we have grasslands in the orange, and we have croplands in yellow. And you can see where the large forests are. Well, we've been deforesting part of the southern hemisphere in South America, and to understand the impact of this, we've been looking at models. And so this is a study by Avisar done in 2004, and it's just an incredibly amazing result, really. So what they show is that we have this in the bottom, the precipitation. And so if we look at the local effect, calling the local effect where it's happening in South America, we see that we have the precipitation before deforestation for cropland and then after. And the after is that red line, and it goes down. Okay, so here's a local impact of their deforestation. But there's this teleconnection that might not seem so obvious, and that's if we look at the impact of this event on what's going on in the U.S., near the Gulf of Mexico and in Mississippi, what we see is that we also have an impact of precipitation changes before and after. And so it shows that this is just one connected cycle, that all these different parts are connected to one another, and it's not as straightforward as it might seem without really looking into the details of it. So I had a lot to cover in a small amount of time, but I hope you got some understanding, some idea about the idea, again, a refresher of the water cycle. And I'm going to leave you with a very complicated picture, one that you can't really draw so easily as you're starting to explain it or refresh your memory for the first time. But what it does is it puts in there all these extra the processes that are going on, and it shows how, now that we've talked about the water cycle, we can even go further if we had the time and start talking about the relationship to the energy cycle, as you see the sun up there driving the radiative exchange or that heating and the evaporation of the water. We've only talked about one small part of this, but one small part of it that we're going to learn a lot more over for the next couple days. So I would be happy to take some questions from you. Thank you very much. Yes?
Hold on. I'm going to bring the microphone since we're taping. Yeah, but we're video.
That's how I feel.
I was just wondering if you could briefly revisit the slide that had a world map and increase in intensities of precipitation, what the meaning of the non-colored areas represents. Australia, that's had 7 years of drought, why is it just clear?
So,
is the prediction that there's going to be no change?
No, so you can see that there's a combination of issues here. That's a good thing to point out, that there are still some unknowns in the water in our modeling. And so what has been highlighted here is that these are the extreme cases that we see, and that these other ones are the ones where there's more uncertainty. So I think if you think about that uncertainty canceling out, then it would predict maybe no change. But it also, another way to look at it is that it could go either way there. And so there's still a lot more to be learned. But there are certainly areas where, because of all of this, we think that maybe there's not, there might not be a lot of change, or on the other hand, it might just be a lack of data. So for much of Australia there, we have not a lot of idea what's been going on. There's not a lot of stations that are of data there.
You said that increased precipitation can bring water back into the aquifers, the groundwater. What effect does the cement that we've covered the earth with, the compacted soil, have on that?
That's great. That's a really good point. And that's, yes, so increased precipitation has the potential to help recharge our aquifers. But if we have we have concrete over it, the built environment can prevent the recharge of it. Now, there's another thing wasn't able to fit into this small, but I'm glad you brought that up, and that's that there's actually an impediment to recharging the aquifers, even in agriculture lands here where we have grain. And that impediment is that a lot of these lands have been what we call tiled. They have underneath them drainages, unnatural drainages that have put in. Where the grains that grow in the Midwest are on all these prairie soils, and the soils themselves naturally were storing a lot of water. We have small changes in the topography, a shallow water table, and in the springs, these land would become very, very muddy. And so what the farmers historically did, and still do to this day, are drain those lands. So there's a lot of land that's being farmed with these tiles. What happens with the tiles is that they're below the surface, and they're like little drainage pipe type things where the water will fall and infiltrate. That's a good thing. So we have water coming through to water the crops naturally. But then they hit these drainage pipes, and that's directed actually to surface flow. And so that's directed right into the Gulf of Mississippi. So all of this grain right here, much of that land is being drained unnaturally more quickly into surface waters. And so even if we have enhanced natural precipitation or just normal precipitation to recharge these aquifers, it's not being done as much because we're diverting those waters. And so that's kind of a hidden thing that we might not think about until you look more closely at the system.
Thanks. Could you say a bit more about what we mean by water use? It's a real problem term because you distinguished between consumptive use and non-consumptive use.
Yeah.
Which is that's fine. But ultimately, I guess most of the water comes around. That the water cycle means that most of the water comes back.
Yeah.
So consumptive water use, for instance, agriculture. You pour the water on the land, but then some of the water infiltrates underground, and presumably you can pump it up again.
Right.
So it's kind of consumptive, but
right.
You can get it back. And then you have non-consumptive use like hydroelectric reservoirs, but you may be losing a lot of water evaporating from the reservoir surface. So that's partly consumptive. I mean, obviously, in a talk like this, you've got to simplify. But I wonder if you could talk just a little bit more about what we mean by water use, and maybe also how good the data is.
Yeah. So that's the consumptive use of it and sort of the non-consumptive use of it. So the borrowed water. The hydroelectric is probably the best example of borrowed water or dams. And you're right to point out that it's not entirely a non-consumptive process because you have a reservoir sitting there. It's exposed to the atmosphere. It heats up, and we're going to have evaporation from it. So we're going to lose some of that water, maybe more than we naturally would have because we're keeping it in a reservoir. But it's going to be used, and it's going to be altered a bit. In some cases, a lot for the thermoelectric, we end up with warmer water. And so it's not considered a consumptive use because we get the water back and it's available for lots of other things. But it's not always immediately back, and it doesn't mean that it's not degraded at all. And temperature can actually be considered a pollutant in that case because the temperatures can affect the ecosystems. It affects the amount of oxygen in a water. The oxygen is directly related to the temperature, and then it's modified by biological use. But for the most part, that water is available again. The consumptive use can be kind of surprising, and I think agriculture, as the question before pointed out, and if we think about agriculture being concentrated in California, is an excellent example of this consumptive use, at least on shorter time scales. So if we think about the path of water from the northern part of California through the Central Valley and out the other end, we have agriculture using that water, pumping for irrigation. It's true that some of this is going to filter down, and then but again, this is going to turn into, they want it to be well filtered. The aquifers there are deep, and the ones near the cities are polluted. So it's mainly surface waters that we're talking about there, and that water is degraded. And it's degraded by the runoff of fertilizers. You can have runoff of nutrients from the fertilizers, even if that fertilizer is manure. So it's not that, say, organic farming versus regular farming is the answer overall, because both can end up polluting in terms of this nutrients. And you also have pesticide runoff. Now, nutrients sound like a good thing. It's kind of a positive word. We all look for nutrients out of our food. But what happens from agriculture is that the nutrients build up in the water, and they're changing the amount that would normally be in there to higher concentrations, and also different ratios of these nutrients. So you end up promoting different ecosystems than would naturally occur. And you end up promoting these, in more cases than not, these algae that form that end up blooming, and then as they rain down, they provide lots of organic matter, and they consume oxygen in the deep waters, and so you've got this odd situation where because you've had so much nutrients, you can't even use them anymore because of this situation. So agriculture is actually a lot of it is a consumptive use. Now, in the Midwest, it's more of a balance in the sense that we do have we don't irrigate the crops quite as the grain crops a lot, and in some places, in other places we do, and we're pumping from the aquifers to do that. We get some natural infiltration, but as I said, a lot of this is diverted to surface waters, and so now you have the surface water, so you have to be using it quickly, otherwise it's going to go out to sea. So all these different reservoirs have different residence times in them, and that's where the consumptive aspect of it comes in. It's consumptive on the time scales that matter to us right now, from the distance from the point of agriculture activity to when it gets back to the ocean and becomes saline again, when it mixes in with everything. And then we have to wait for the water to come back through the water cycle again. So runoff can be a degradation, and it can also just enhance this natural cycle of delivering things back. Now, it isn't consumptive on the very long time scale, so if we go to a very long time scale, well, we're going to get that water back. So we haven't entirely used it up. It means that it's just taken out of it on this shorter time scale. So you have to remember that part of the equation. I don't know if that gets at what you, yeah.
So I want to remind everyone that the slides will be available online, including that water cycle slide, and you can print those off as individual handouts for your students. We have about 10 minutes left. Does anyone want to share how they've maybe taught the water cycle in the past? Any successful examples?
Just a comment. Excellent presentation, nice visuals. Even I could see that from this far off with my glasses. That's great. So one of the things is I think is important how humans are affecting the water use also, because the recent oil spill and what kind of an impact it's going to have in terms of transport of this VOCs and all the recalcitrant type of compounds into the environment, and also the use of chemicals that we are just using for our own comfort, how these are entering into the water cycle, and what kind of impact it's going to have. The so-called precautionary principle that we don't know the effects of these compounds, even in micro quantities, on human health. After all, we are using these compounds for our comfort, and then in turn, probably in the long run, what kind of an impact it's going to have on the water use, and how much of water is going to be really available for human consumption for that particular use.
Yeah,
Can you make some comments on that?
Yeah, I mean, so over the next few days, if we look at the titles that we'll be seeing, we're going to be seeing a lot of these different case studies. And I guess I would have loved to be able to give the talk about the impact, but I wanted to start out at least setting up something about the natural cycle. But I think the important thing to think about is this framework idea and the natural cycle. And as we learn about these different case studies and the things we'll be hearing over the next few days, to really try to think about, okay, so what is the beneficial part of that impact that we have, but what is the consequence as well? And can we put that into this framework of degrading quality, and how is it affecting the quantity? And then what are the impacts? Because we have direct human impacts, and particularly, when we think about all these different chemicals that are in the environment at very small quantities that haven't been very well investigated often, we don't often follow that precautionary principle very well. And we also have the environmental impact of that. And in some cases, the environmental impact of that could be the canary in the coal mine, saying, okay, look, we see this impacting the environment. We see effect of the atrazine on frogs. Atrazine is a pesticide. And we see that it's affecting the endocrine system of frogs. What is it doing to us in small quantities then? But then there's also the aspect of the larger impact of the environment beyond that implication of direct human health, but on simply decreasing biodiversity and changing the landscape, desertification of areas. We looked at the model results of the deforestation of the tropics. And so there's a lot of different ways to think about these environmental and human impacts. And I think it's great to point that out now, to think about these human impacts and to think over the next few days, okay, so if this is the natural cycle, how have we changed it, or what are we doing to change? And that would be, when I looked through, I guess, lesson plans, so I tried to look through what was out there and tried to put some things in here that combines maybe some of the different lesson plans that I see, but also highlights some other ideas. I think what sometimes is lacking is this connection between what it ought to be and what we've done now. And so if you can take just a little bit of the thinking about what it ought to be in terms of these natural to the impact over the next few days, that would be just a wonderful contribution to walk away with from this.
Thank you so much. Please join me in thanking Dr. Pamela Martin again.